Hopefully he's okay that I told you that. So I'll do a slight kind of recap of where we left off talking about confidence intervals on Friday. I don't know if we'll get to Excel today, but I might start showing you how we do this in Excel, work through some problems in class. But the idea was, we said, if I know that the distribution of my sample means is going to be normally distributed, and we said the mean of our sample means, or where is it centered around? It's normally distributed around that population mean of the data we sampled from. Okay? We also had that the standard deviation kind of said was just the variance of the original data we sampled from divided by the sample size, and then we take the square root. So if, excuse me, we look at the standard normal distribution, kind of the example that we had was we said, well, look, I know that if I want the area in the middle of this distribution to be 0.95, I've got two equally sized tails. The area under the curve is 1. It must be that there's 0.025 in each tail. Or I kind of introduced this idea of alpha, right, at the end of the class. And alpha, all that was the area outside of our confidence interval that we wanted, but in decimal form. So if I wanted a 99% confidence interval, alpha would be 0.01. So half of alpha in each tail would be there, would be 0.005. Here, I wanted 95% in the middle, and that 5% was outside the interval, half on each side, 0.05 divided by 2, 0.025. We can then use that inverse process, look at that standard normal distribution table, figure out what z value would give me 0.025 in the tail. We said that ended up being negative and positive, kind of 1.96 here. All right. So that told us that there's a 95% chance I see a sample mean somewhere in this range. And if I build a confidence interval around this, where I go 1.96 standard deviations to the left and to the right, that confidence interval will include that true population mean. Any sample mean I see here, when I build that confidence interval around it, will include that population mean. Now, if I get a sample mean that's way out here, more than 1.96 standard deviations away, well, then I would have a confidence interval that didn't quite include my population mean. So I'm going to be right with my confidence interval 95% of the time. 5% of the time, I'm going to be wrong. Right? Now, the only thing that's going to change when I'm building confidence intervals of different levels, well, my sample mean value would still be the same. The original variance of the data and my sample size are the same, but I can build different levels of confidence depending on what I want alpha to be. Right? So I can build a 99% confidence interval. I can build a 95% confidence interval. I can build a 90% confidence. I can build whatever level I want, but those are the three that we typically kind of use. Excuse me. So I think if there's anything else I want to say here before I jump into it. So that was kind of the idea behind what we were doing. So let me see if I get this to work right. There we go. So kind of to write, how do we come up with our confidence interval? Well, it's whatever z value gives me alpha over 2 in each tail. Right? Alpha was the total area one of the tail. Alpha divided by 2 is how much is in each tail. We then would use the inverse process to look up that number of standard deviations the way we need to go. That's what that is. Then, if the z-score tells us to go 1.96 standard deviations away, well, 1.96 times the standard deviation. So I could rewrite this a little bit, because I have an equation for that standard deviation of my sample means, which was just the square root of the original variance over my sample size. Okay. So that's kind of the general form, and we kind of remember here, I can do this in steps. I could calculate this ahead of time, then just have one value to plug in, or I could do this all on one line. Okay. Now, when I add, well, I said I was going to call this the margin of error, right? When I add that margin of error, it's going to give me my upper bound. When I subtract that margin of error, that gives me my lower bound. So a confidence interval is always going to have like two equations. You're going to have two values, an upper and a lower bound. right? That's kind of telling you the range, right? That you know with whatever level of confidence you chose, that the true population mean is somewhere in that range of values. And you can say it with whatever that level of confidence is, right? 95, 99, 90, and kind of those corresponding alphas. Okay. Any questions on that? Let's go through some actual values to this. Right. So let's go back to this birth data and say, okay, I can kind of cheat because I know what the population data looks like, but I'm just going to take a sample from it. Okay, so I somehow know, and this is where to start out very hokey, right? We're going to assume that we somehow know the population variance. How the hell do I know the population variance if I don't know what the population mean is, right? If I just have a sample. To give you somewhat of an explanation why this actually could be practical, a lot of times when it comes to like production process, right? You might know the variation that exists in the machinery, like just because of physics, I don't know, material science and things like that. But you can't test every single product, right? So you might be only able to have a sample and test the products to make sure you're seeing the mean that you want. And you don't have the population data, but you know because of some outside science, the population variance on your production process is a certain value. So that would be kind of the explanation. Now, we'll eventually, I don't think we'll get there today, but on Wednesday, we'll start talking about a different distribution, which is kind of very similar to the standard normal, but it's called a student T distribution. And that will be more practical where what happens if we only have a sample variance. But for now, makes it a little bit easier if we have the population variance and we got to kind of walk before we can run here. Okay? So we somehow know that the population variance of the length of pregnancy is 9 weeks. We take a sample of 81 births and we see that the average to the length of those pregnancies was 38 weeks. What's the 95% confidence interval for this? Okay? So once again, the first thing I want to think about is we're kind of working in the inverse when we build confidence intervals. So we start with that standard normal. We need to find the z-value that gives us alpha over 2 in each tail. So if I want the 95% confidence interval, I should use different numbers to kind of review. But what would my alpha value be? So if I want 95% confidence, what area is outside my interval? 5%. In decimal form, 0.05. Now I have to remember a confidence interval has an upper and lower limit. There's areas on both sides. So I've really got, you can kind of think about two tails, right? Or two sides to this confidence interval. So I've got half of alpha in each side. So that'd be what? 0.05 divided by 2 or 0.025. Okay. So when I go to my standard normal table, which I conveniently forgot to pull up earlier. Oh, where's it at? There's my T tables. Did I not move this anywhere? Here it is. So I'm working in the inverse. I know the area I want the tail. So this is where, when I look up 0.025, remember the probabilities from this table are always the area to the left. So when I look up 0.025, I'm actually looking up the left tail. So I'm always going to find a negative value when I've got really small alphas, which, like I said, benchmark 90, 95, 99%, those alphas would be 0.01, 0.05, 0.1 divided by 2. So very small values. So sure enough, I look up 0.025 here. Okay, this is a nice one because it's one of the exact numbers in the table. That corresponds to a z-value of 1.96. All right, so kind of go down here, find that probability or that area you want in the lower left tail, alpha divided by 2, the corresponding z-value, 1.96. Okay. Now, that's negative 1.96. When you go to that confidence interval formula, notice kind of the positive and the negative are already built in there. So really what you're wanting to do is go 1.96 standard deviations above to get your upper bound, and then 1.96 standard deviations below to get your lower bound. Okay? But when in practice, when you look this up in the table, you are going to get the negative value. You just have to remember, like, Oh yeah, the negative and positive, they're already kind of built into my confidence interval equation. So I'm just using the table to get what that number of standard deviations away I need to go is. Is that clear? Questions on that? Okay. So from here, once I get that z value, it's just a matter of plugging in our values, right? So we'll go back to the problem here. Look at these possible answers here because I want to make another point. So what I'm going to do is I saw a sample mean of 38, right? That's my sample mean. I should be building my confidence interval around that. So what should always be true is that your sample statistic is exactly in the middle of your confidence interval. So here, I don't think any of them you can rule out because it looks like 38 is exactly in the middle. But let's say, I'll do this sometimes. Let's say I told you that, one of the possible answers was something like this. Well, right away, that can't be right because this doesn't even include the sample mean you saw. Remember, the whole point of what we're doing is we're basing our confidence interval on the sample mean because that's the best guess that we have about where that true population mean lies. Okay? So we're going to base our confidence interval around that sample mean. And from there, it's just take that sample mean, right, 38. To get our upper bound, we would go 1.96 standard deviations away, right? That's what we found earlier. And then what's the standard deviation of my sample means? Well, I can do this all on one line. That's the square root of, I think the original variance we said was 9. And I had a sample size of 81. All right. So it's just a matter of plugging my values in there to that confidence interval equation. All right. I'll be given that population variance. I'll know my sample size. I'll find a sample mean from whatever data I have. And then it's really the only process, the only remaining part of the process is to look up how many standard deviations or that z value we need to go. Yeah, so remember, we're going a certain number of standard deviations away, but we're looking at the sample statistic of a sample mean. So it's this many standard deviations times the standard deviation of my sample means. But the standard deviation of my sample means is the original variance divided by my sample size, and then we take the square root to get that into standard deviation. Now you could do this, like break this down. So maybe I want to do like, what would this be? So this is 1/9. This is what, a third. If I do that. So you could calculate that standard deviation ahead of time, and then all I have to do is plug in the one value. Right? So kind of breaking it down to intermediate steps can kind of be helpful, especially for some stuff that we do further down the road. Kind of breaking that down, calculating that standard deviation of the statistic you're interested in first, then you just have one value to plug in there. Okay. Any other questions on this before we keep moving here? So, right, we identified kind of what we were given from this problem. Alpha was the real important thing there. The other things I think are pretty easy. We then looked up that z value that gave us alpha over 2 in each tail. Here's the intermediate step. I could calculate that standard deviation of my sample means ahead of time. Then I only have one value to plug into that confidence interval equation. And then it's just a matter of getting those values plugged in. When I add that margin of error, I get my upper bound. When I subtract it, I get my lower bound. Okay. So do a slightly different one here. I want to see kind of how you guys are getting this. So you're going to have that z table. So think about if we instead had a situation where I wanted to build a confidence interval, like somebody took an example, but there's a reason why I'm using it. Let's say I go over to the rec center, I grab 35 of the 45-pound weight plates, and I find that there's a sample mean of 46.5. Right? So, whatever the production process, yeah, they are 45 pounds, but the pouring, the different materials they're using, it's not uniform. So some of them weigh a little bit more than 45, some of them weigh a little bit less. I find the sample mean of 46.5. I somehow know that the machinery, the variance on that process is 25. So this is kind of like my population variance. I've got my sample size, I've got my sample mean, I've got my population variance. The only other thing is, well, what level of confidence am I building this confidence interval for? So if I have an alpha of 0.1, what would my confidence level be? Yeah, so 0.1 is the area outside of my interval. The area inside would then have to be 0.9 or 90%. Okay. So kind of given these values, give you a little bit of time to kind of come up with a lower and upper bound here. Now, once you find one of them, I didn't repeat any of them, so you really only have to either calculate the upper bound or the lower bound. But in practice, you need to do both to know exactly what they are. And we'll kind of talk about it here in a couple minutes. So talk to the people around you, kind of work with each other, kind of come up with this, and then we'll kind of reconvene. Take your best guess here. We'll kind of talk about these. Give you a little bit of time to get your responses in. All right, everybody get best guess in here. Got 9 of you here today. I don't know. You're good. Talk to me after class. So, everybody got their responses? All right. So close this out. Okay. So first of all, 2 of these I can rule out right away. Which 2 can I rule out? Now, one of them is harder to kind of identify why I can rule out than the other, but I can rule 2 out.
D, because the lower option is higher than the.
Yeah, right. Remember, we're building our confidence interval around this value. So not only does this value have to be in my confidence interval, it has to be exactly in the middle. 46.5 isn't even in this confidence interval, below the lower bound. It doesn't make any sense. Another one I can rule out. Like I said, it's a little bit tougher to see. But if both of these have the same lower bound, but different upper bounds, 46.5 can't be exactly in the middle of both of those. So if I look at that, 46.5 is about 2 away from 44, but it's about 3 away from 49.45. So that one, it's not exactly in the middle. I know B can't be the answer either. Now from there, we have to go back and figure out, okay, my alpha has changed from the previous problem. So I no longer want 0.05 outside of my interval. I want 0.1, right? So if alpha is 0.1, how much is in each tail? I can put this area. 0.05. Yeah. I already closed it out. So 0.05, right, is going to be the area that I want in the tail. When I go to look up that up in the Z table or standard normal table, what value do I find? Anybody get to that? Yeah.
1.65 or negative 1.65.
Yeah. So if I go here, 0.05, looks like I'm in between these two. It's as close as I can get. So negative 1.6. If we go up here, in between negative 1.64, negative 1.65. We said if we're kind of using the table, we'll always use the higher of the two in absolute value. So if it's negative, we'll take 1.65. So, all right, we need to go 1.65 standard deviations away. Now, here's where it probably makes it a little bit easier to just calculate this ahead of time. So our variance was what? I already forgot. 25. So the square root of 25 over 35. I don't know exactly what that ends up being. All right, you could come up with that value ahead of time. So I think I probably got that in the slide. So we can see what that value is here in a second. So about 0.845, right? I'm rounding this to the other decimal. 0.8452. Now I've got everything I need, right? I had 46.5 as my sample mean. I need to go 1.65 standard deviations away. And the standard deviation value is now whatever, not 82, 0.8452, right? Now it's just a matter of plugging those values in to kind of come up with my upper and lower bound, right? Add that margin of error to my upper bound, subtract to get my lower bound. So if I do that, I get this. Okay. Any questions over any part of this process or anything that's kind of tripping you up? Any questions? So really the key kind of, I think the toughest part of this is looking up that number of standard deviations where you need to go or looking up that Z value. Well, other than that, it's just a matter of plugging in the values that you're given into that formula. So I want to do a little bit more with the interpretation of confidence intervals. Okay, so why are they useful? Here's a good case, and this is a very stupid example where I'm looking at weight plates, right? But I'll try to make the application seem a little bit broader. So if I am working at this company and I sample 35 of this product that we're making, and I figure out with 90% confidence, the true population mean of this product is somewhere in between 45.11 and 47.89. Why is that an issue? They're supposed to be what? Started out with. They're supposed to be 45-pound weight plates. So based off of my sample, I go to the company and I say, your product with 90% confidence, I can tell you the true mean of your product is not what you want it to be. It's not 45 pounds, right? And I mean, the lower bound is just barely above that. I know it's close, but 45 is not one of the values in that range. Now, this seems trivial if we're talking about like weight plates, but you can imagine like if this is a pharmaceutical drug and I'm measuring, you know, the amount of whatever the drug is that's in my pills, and I find that it's, you know, above or, you know, not above or below a certain milligram, this is a huge issue, right? Or if I'm building steel beams, right? They're supposed to support buildings, and I come up with, based off my sample, that the confidence interval doesn't include whatever that level of the material I need is, that's a big issue, right? So this is kind of a trivial example with weight plates, but it really would go on to anything you could measure the weight of, or like I said, like with drugs, like milligrams of whatever the product is. You know, you can almost imagine like using confidence intervals for like to figure out false advertising, right? Whatever, you know, if I take a sample and it doesn't include that value, whatever the product says, well, then whatever level of confidence I can tell you that does. Now, here's one thing I want to point out here, because what if instead, so I could say, I can go to that company with 90% confidence. I could say, your product isn't matching up with what you said. But I could just have a bad sample, right? I could have had, well, I don't have it drawn up here, right? But we said, I could have like the sample mean out here, where even though my confidence interval doesn't include that true, that could be one of my errors, right? So I'm saying with 90% confidence, I could be wrong 10% of the time. And so the confidence being wrong 10% of the time, we're not going to take what you said. So I go, okay, I can tell you with 99% confidence. The only issue is if I want to say this with 99% confidence, what happens? Well, I still have the same sample mean, population variance. I'm taking the same sample, so it's the same sample size. Nothing has changed in this equation except for if I want to say with 99% confidence, what's going to have to get updated. So before, we were using an alpha of 0.1. At the 99% confidence level, alpha would be 0.01. So if instead of 0.05 in the tail, I want 0.005, what's going to be true about the number of standard deviations out I need to go? Well, if the area to the right of 1.65 is 0.05, to get the area to the right to be 0.005, I'm going to have to go a higher number of standard deviations away. I think if I look this up, well, I'll probably get it wrong. I think it's 2.58, right? If I look this up in the table. Well, now what happens? If I put 2.58 here instead of 1.65, what's going to happen to the width of my confidence interval? If this number goes up, I'm going to be adding and subtracting a larger margin of error. So my confidence interval is going to get wider. Right? Well, I don't have a lot of room left. If this gets a little bit wider here, now my lower bound probably does fall below 45. And I couldn't tell this company with 99% confidence that their product isn't weighing exactly what they want, right? I don't know what the exact number is going to be. I'm just guessing that once I put 2.58 in here, I'm guessing that lower bound ends up being a little bit below 45. Okay. Any questions on that idea? So intuitively, when we're thinking about saying things with different levels of confidence, here's a good way to remember it, right? If I just give you a wider range of values, like let's say with 90% confidence, I can tell you the true average income is in between 40 and 60,000. Well, if I then tell you, the average income is somewhere in between 20 and 80,000, I can say that with more confidence because I'm having a wider range of values, right? That's all that a higher level of confidence does. It increases that number of standard deviations out we go to build our upper and lower bound, and it just includes a higher range of values. So of course we can say something with a higher level of confidence. Now, sometimes it doesn't matter, right? We can create this pretty wide interval, and if it doesn't include these interesting values, like it didn't include 45 even at the 99% level, well, we could, be able to make our statement with a lot more support, right? Saying something with 90% confidence isn't as good as being able to say it with 99. But the idea there is that if we want to say things with a high level of confidence, our intervals are going to have to get wider. And we kind of see that taking place if we're just thinking about the area that we want in the tail is getting smaller. So we're going to have to go a higher number of standard deviations away. Okay. So what changes these confidence intervals? We'll go through this kind of quick. I already mentioned one. All right. If we want to say something with here I'm saying it backwards, right? So I said if I want to say something with a higher level of confidence, the interval will get wider. So if I want to say it with a lower level of confidence, that means that I'm having a smaller area in the middle, larger area in my tails, or a larger alpha value. Well, if I want a larger alpha value, it's like I'm working this way, but I don't have to go as many standard deviations away. So if I want to say something with a lower level of confidence, I'm getting kind of this more narrow interval. If I have a higher sample size, well, I'll come back to that one. If my original data has a higher variance, let me write this out so we can maybe see this a little bit easier, I think. So let's say I wrote the confidence interval equation out instead of breaking it down into steps. If I have a higher variance from my original data, well, then the standard deviation on my sample means is also going to have a higher variance or a higher standard deviation. So a higher variance in the original data makes my margin of error larger. So if I'm adding and subtracting a larger value, I'm going to get a wider or a larger interval there too. Now, the one thing that as a researcher you can influence, you can't change the population variance, right? It is what it is. You can't change what the sample mean you find is, right? The data is what it is. But what you can do is take a higher sample size. Right? So why is that important? So if I'm thinking about, let's say, I don't know, I had a sample size of 35. Here's the distribution of my sample means. Right? Well, what happens if I take a sample of, so you can use it for coloring. What happens if I take a sample of 100 or a higher sample size? What's going to change about the distribution of my sample means? Still going to be centered around the same value, that true population mean. But what's happening to the standard deviation of my sample mean? If the sample size is going up, then that standard deviation is actually getting smaller. So why is that a good thing? Well, because it's way more likely that I'm going to get a sample mean that's really close to the population mean. So when I have these high sample sizes, I know that whatever sample mean I'm seeing, it's very likely it's going to be pretty close to that population mean. And because I know that standard deviation has gone down so much, even building the same confidence level, right, 90% or not, whatever it is, I'm going the same number of standard deviations away, but my standard deviation might now be, instead of 5, might be 0.25. So when I take these higher sample sizes, my margin of error gets smaller. I'm adding and subtracting a smaller value. I can really pinpoint down where that population mean is. I can create a pretty narrow range of values, right? So higher sample sizes, once again, it will kind of come out for the rest of the semester, but always better to have these higher sample sizes, right? And it kind of makes sense. If I only have a sample of size 10, that sample mean won't be near as useful about where the population mean is if I have a sample of the size of 1,000, right? I've got way more data. It should be more informative about where that population mean is. So I really can kind of get this narrow range of values, right? Or a pretty small or narrow confidence interval, okay? Questions on that before we keep moving here? So I think I'm going to switch this up a little bit. I think my slides are out of order, so I don't think it's out of order for what I want to do right now. So the next thing that we would talk about is if we can build confidence intervals for sample means, we can do the exact same thing for sample proportions. Okay, so a little bit of a kind of just introduction to that, just to kind of see how they'll match up, and it really won't be that. Really won't be any a lot more difficult. So whenever we build a confidence interval, we can do this for all kinds of statistics. Here, we're just doing it for the sample mean. I could also do it for my sample proportion, which just means I'm going to base my confidence interval not around my sample mean, but around the sample proportion. Now, I said on Friday, the sample proportion is just a unique case of the sample mean where the original variable was what? Remember what I was saying there? So when coming up with a sample proportion, it just means the original variable was 1, 0. Right? So then when I took the mean, it really represented there was this many people who had the 1 kind of value for that variable divided by the total number of people. So this would be like counting up the number of people that had blue eyes out of everybody, right? That gives me my sample proportion of people with blue eyes. Okay. Well, I'm then going to still have my margin of error that I add or subtract to either side. Remember, this represented the standard deviation of my sample means. Right? So to build my confidence interval for the proportion or the sample proportion, I still need to figure out how many standard deviations away do I need to go. And there, that doesn't matter. The statistic doesn't matter because I'm still going to be using that standard normal distribution. Right? As long as I get that sample size over 30, I know that I can use that standard normal distribution, or the sample means will be normally distributed, so I can figure out how many standard deviations away I need to go. Well, this is the number of standard deviations away I need to go. I need to then multiply that by the standard deviation of the statistic that I'm now interested in. Well, the statistic I'm now interested in, you have to kind of remember, we calculate the standard deviation a little bit differently, right? We aren't just necessarily told that population variance, but we can calculate that by, we know it's just going to be p times 1 minus p, right? And then we'll divide that by our sample size, similar to how we did it for the sample mean. Okay. So procedurally, nothing's really going to be that much different. We'll calculate the standard deviation a little bit differently, but we're still going to look up that z-value the same way. It's going to be the z-value, the number of standard deviations that gives us alpha over 2 on each side of our confidence interval. We're building our confidence interval around the sample statistic that we're interested in. procedurally, it won't look a whole lot different. Right? Now, one thing I'll throw in here, I kind of glossed over. When I'm building this confidence interval for where the true population proportion is, so I don't have the true population proportion. So when we're doing confidence intervals for proportion examples, the best guess that we have, or the best information we have about where that population proportion is to use our sample proportion. We kind of show that there's a mathematical proof that that's okay. Technically it won't be, it's going to be a very, very close approximation to a standard normal distribution, which is why we can still use it, as long as we have a sample size over 30, right? So using that sample proportion shouldn't kind of be an issue as long as we can get that sample size to be over 30. Okay. And don't worry about this, it's me being complete. There's some other stuff that we're not going to kind of deal with in this class, but essentially what this is saying is you need to make sure that you have extremely low or extremely high probabilities. Sometimes that means that you have to take a higher sample size. You can kind of imagine, like, let's say that adverse reactions to drugs are 1 out of every 50,000 people. Well, I could take a sample of 10 people or 35 people, and I'm not going to see anybody have an adverse reaction. So if that probability is really, really small, I need to make sure that I have a pretty high sample size. Right. So that's all that's saying, but I'll never kind of give you examples where that's not true or trying to trick you. And for the most part, we have large enough data sets where we don't have to really worry about this, no matter how small that probability is. Now here is where that margin of error is actually what it's called. Like I said, I'm being a little bit loose with that term when I use it to refer to what we add and subtract the sample means, but just to kind of keep it consistent, we just think about what we're adding and subtracting to our sample statistic. That's going to be our margin of error. Okay. All right, so I think I'm going to hold off. If we have time today, we'll kind of work on a few problems, but this kind of sets us up where we'll kind of start working on some problems on Wednesday. I want to show you a little bit of how we do this in Excel, because I think once we see this in Excel, I can maybe give you some support for what we're doing that might help make a little more sense. So under the in-class data folder, I believe I put this median rental price data set. Okay. So I went out and grabbed this the other day. It's got, I guess the last kind of month was 2019 in December. We've got a bunch of data here. I guess I should have cleaned this up. If you want to, kind of one nice, easy way. If you hit the home button, it should send you up to the top. But if you use that Control Shift, you don't only have to use it to select things. You can use it to like move over as well. So then, okay, this is the last column. I'm going to move over here. Okay. So once you open that up, kind of scroll up to the top. If it's easier, you know, once you're, if I hit, where's my home button? I don't even know. Shift. All right. So if you hit your home button, it should send you right back up to A1. If I then click here, Control Shift or Command Shift on the Mac, hit the over arrow, it's going to send me over to this last column. Now I can kind of do my work over here. Okay. Anybody have any issues with that? Yeah.
I just can't, like, my Wi-Fi just stopped.
Oh.
We need to get like,
I'll give you a little bit. I'll wait a little bit.
no, it's okay.
I know the Wi-Fi in this building is a issue, to say the least. Okay. So I've got this rental price data, right? And I've got a bunch of cities here. I don't remember how many exactly, but if I wanted to, how could I pretty quickly find my sample size? What equation in Excel could I use to do that? And actually, before I get going here, probably be helpful if you guys could see this a little bit easier. Huh? There we go. All right. So what equation could I use to find my sample size pretty quick? I've used this before. I just want to count the number of observations. Count function, right? So I'll go over here, select that first cell, hold Control Shift or Command Shift on a Mac, hit the down arrow. I should select my entire column. I'll hit Enter. So this is where this is very helpful on a laptop. Instead of scrolling all the way back up and closing my parentheses, if I just hit Enter, it closes it and sends me back. So that's great. So almost 1,700 observations. If I want to be a little bit more helpful here, I'll add in this, right? So my sample size is my lowercase n, right? That's what that represents.
Are we gonna assume these are sample instead of population?
Yeah, so this isn't every city. I've just got a sample, right? There's more than 1,700 cities in the US, so I've just got a sample of them, right? So the next part, and this is where it gets a little hokey, I'm going to kind of have to give you a population variance. So for me, I'm going to treat this, I'll just use an old month, right? So actually, I'll just give this to you. So this is just getting an idea. In like a problem set or something, you'd have to be told the population variance. So I'm just going to tell you that it's 1,800 just for the sake of this example. You can't really calculate this because you don't have the population data. So this is kind of like the idea, the production process has a certain, so this is going to have to be something given to you. We'll see that in practice. If we can only calculate a sample variance, we can still build confidence intervals. It just throws a little bit of an extra wrinkle into it. So I think we'll probably get there on Wednesday. In fact, before I forget, I put up another table on Canvas, T-tables, right? So we'll start using these on Wednesday. So similar to the standard normal, if you want to print those out or make sure you're able to pull them up in class, we'll be kind of using those in class as well, okay? So that's a little bit of foreshadowing. So we'll go back. So we have this known population variance. For now, who knows how we got it? It was given to us, okay? The only other thing that we need for our confidence interval equation is our sample mean, right? Well, I can find that pretty easily. That's my average function. So just average function, select that last column of data. Okay, perfect. From here, I could actually calculate 3 confidence levels pretty quickly, right? And our 3 benchmark confidence levels, so I'll do here, confidence level. We'll do the 90, the 95, and the 99% level, okay? These would correspond to alpha values of what? So my first alpha would be, 0.1, right? There's 10% outside my interval in decimal form, 0.1. 95%, my alpha would be, saw someone mouth it, 0.05. And then my last one, 0.01, right? So I've got 3 alpha levels now. And at each one, I want to find my upper and lower bound, okay? Also, to widen these, I think I've told you this, but if I haven't, if you just double click, it like auto fits so that, I don't know, just a little bit easier to see as you're working on things. So I'm going to kind of do this in steps because I think it's kind of how we would do it by hand. It makes a little more sense. So up here, I'm going to find the standard deviation of my sample means, okay? Because that's something that I can use, right? Instead of typing this formula all into one line in Excel, I'm going to break it down into steps, kind of like I said, can be helpful when we're working through these by hand. So all that standard deviation of my sample means is I take the square root of what? My original population variance, which once again, I had to be told that, divided by my sample size, okay? So I'm just calculating that ahead of time. So then when I get to building my lower and upper bound, I just got one value to select there. So I go down here. Well, how would I find my lower bound? I'm just taking my sample mean. I'm subtracting the number of standard deviations where I need to go. Okay, well, this is another thing where I don't have that Z value yet. So I'm actually going to insert a column here. So I just clicked on this column, right clicked, I'm going to insert. Right? Because I need to know that Z value, okay? Well, how can I find that Z value? I know it's the value that gives me alpha over 2 in each tail, right? So how can I use Excel to find this for me? Well, in practice, we use the table, right? By doing this by hand, we were working in the inverse process. So this is why I showed you one of these functions before. we're using that standard normal distribution, so norm.s, and we're working in the reverse or the inverse. So norm.s.inv, all we have to tell it, what's that area that we want in that lower left tail? Alpha divided by 2. Now, one problem with doing this in Excel is when we look this up in the table, we said we're always going to get the negative z value. So if I hit enter here, sure enough, I get that negative. I can be more precise. It's not negative 1.65 now. It's 1.64485. The problem is when I start building my confidence interval, the positive and negative sign are already built into that lower and upper bound equation. So I just want the absolute value, right? So to kind of drop that negative sign, I can just take the absolute value here, and it should drop that negative sign for me. Okay. Now, if I want to copy this down to find that number of standard deviations away I need to go for the next 2 levels, what's the problem going to be? Well, no problem, really. This cell reference would just update to my next alpha. So I could copy this down, and I've got my 3 alpha values. Notice it's not technically 1.96. It's very, very close. That was the value that we looked up in an earlier problem. But we should see the same we should see a more precise value of what we're finding in the tables. Okay. So anytime I want to build a confidence interval for the 90, 95, 99% level, it's always going to be these same 3 values, right? So you'll have this template to look at. I'll put it up on Canvas. I apologize. I didn't get to grading your individual assignments. I should have those done before Wednesday when we meet, but I'll probably get up the next Excel assignment. There's going to be some stuff in there that we haven't done yet, but based as we start chipping away at things, you'll start getting be able to get a little bit further and further into it. So I'll get that up there this afternoon. Okay. So those are those 3 Z values. Now it's just a matter of using Excel to be our calculator. Take my sample mean, subtract this many standard deviations, multiply that by, well, what is the standard deviation of the statistic I'm looking at? We calculate that ahead of time. That's up there. Okay. It's as simple as it is. All right, we're using Excel to be our calculator here. Right? So if I want to copy this down, what's going to be the issue? The only thing that should change when I want to say things with a higher level of confidence is that Z value. So everything else, I want to freeze those cell references. So here, I'll freeze these, or if I want to, I could use that shortcut F4 or Command T on a Mac. Okay. But I don't want to freeze that Z value reference because when I copy that down, I want that to update. Okay. So I'll hit enter here, copy this down. I've got my 3 lower bounds pretty quickly. Okay. Now to get my upper bound, if I copy this over, it's going to update my Z value cell reference. I don't want that to happen. So kind of a nice thing if I want to copy something and I don't want the cell references to update, instead of freezing it and then going back and then unfreezing it, if I just click on the cell so I can see the formula and then I double click so it selects the whole formula, I'm going to either use my shortcuts or Control C, or I can copy. To get out of the cell, the easiest way is I just hit enter, gets me out of the cell. I'm going to go over here, paste it. Notice I get the exact same value. When I copy and paste that way, it doesn't update cell references either. Right? Now that's helpful if I just want to have a long equation. I don't want to type it all out again. What's the only thing now to get my upper bound that I need to change? I'm taking my sample mean, subtracting the number of standard deviations away times whatever that standard deviation is. For my upper bound, I don't want to subtract. I need to add that margin of error. Okay. So I'll hit enter here. Now I can copy this down. And pretty quickly, for 3 levels of confidence, I've been able to get my upper and lower bounds. Okay. Want to see any of those cells again or have a question over anything there? Now, if you wanted to, you could have made this part of your equation down here, right? You could have, didn't have to break it down into parts. In fact, you don't even have to do the Z values. You could have built that into the cell as well. I just think it's helpful to break this down into parts to make sure everything's working correctly, right? But you'll notice these are really, really small intervals. Why are they so small? What's one thing we said made these intervals really, really small? Yeah, I've got a high sample size, right? So that's going to drive that standard deviation. Even though the original variance started out as 1800, Well, if I get almost 1,700 observations, I can drive that standard deviation to be really low, right? So now when I'm going a certain number of standard deviations to the left and the right, that's not going to be very far. And I get this really nice narrow range where I can say, based off my sample, the average rental price at the end of 2019 was somewhere in between $1,928 and $1,931. I get a really very narrow range of values, which this is also terrifying, but right, like it's that high. But you know, we can do this with any data set, build these confidence intervals. We'll talk about how we do the sample course on Wednesday. I'll show you how we do that in Excel, and then we'll move on to talking about the more realistic student t distribution where I'm not given some population variance. I can only use the sample variance that I can observe. Okay. All right. If there's no more questions for me, I'll let you guys get out of here, and I will see you on Wednesday.